Okay, so welcome. How I wanted to set this up was to simulate the idea of having a PowerPoint going along, kind of to show certain things, and then to have a Go playground going on at the same time that we can code things in the browser and show examples for. Okay, so this is somewhat experimental, and again, as I said, I'd appreciate any feedback that you might have on how this setup kind of helps you learn, and if you think it's effective, or if not, what you think might be lost in the process. So I'll go back and kind of start and do a little review of where we had started talking about last time when we started talking about functions. So with functions, in the mathematical world, we think of a function as a rule for mapping input values to an output. So for the function f of x is sine of 20x plus 10 of cosine of x plus x, this is an example of a function that takes one real number as input and as output gives another real number. In mathematics, of course, we could have multiple inputs, so we could take x and y as inputs to our function g. Here for this function, which is sine of 20x plus 10 cosine of y, we would have a single number as our output, which would be, for example, the height of this function shown on the right. Or we could have multiple outputs. So we could have a function in mathematics that takes 3 or 4 inputs and returns 6 outputs. This is a very generic definition of a function. And we think about a function in computer programming as the same general idea. So we have an input. It goes into an algorithm which may include multiple functions, each one of which has an input and an output. And then the algorithm produces an output as well. Okay? So the idea here is the same. The function syntax in Go corresponds to having a function keyword that indicates the start of the function. Then there's a function name. We have a set of parameters as well as the types that they have. Then we have the return type of whatever the variable is that we're going to return. We have brackets that are used to group the start and end of this function. And then we have a series of lines that indicate what the function does on the input and how it returns the appropriate output. So this is just a simple function that would be a function that takes an integer, x, and returns x squared. Okay, so we could put this in Go playground, function. The name of the function is square. It takes a single parameter x, which is an integer. It's going to return x squared, which is an integer. We need to provide brackets around it. And again, it returns x times x. So now we can call this function from inside of main. We could declare a variable if we wanted as z equals 3, which has the integer type that we know from last time. Or we could have said var zint equals 3. And we could declare a variable y to be equal to the result of squaring z. And we can print the result of y, which then should be 9. Okay? And we'll notice then that this doesn't, of course, change the value of z, which should still be 3. The value of z was copied over when it was passed into the function square. So if we run that, we should see that we still get a value of 3. Okay? So functions can be called inside of main. The result doesn't change if we put the functions after main. Go will know to detect these and to run main as the runnable part of the program. Functions can even call each other. So we could define a function, let's call it 4th power of x as an integer that returns an integer. Okay, and this is going to return x to the 4th, which is x times x times x times x, or just the square of x times the square of x. Okay, and so we could print, say, the result of taking the 4th power of our variable z, which should give us 81. All right, so functions can call each other. They don't have to just take one parameter. We could have, say, a polynomial type function or a quadratic function that takes an a variable as an integer, b as an integer, c as an integer, and x as an integer. And it's going to return an integer corresponding to doing the process ax squared plus bx plus c. So we could say return a times square of x plus b times x plus c. And so in fact we could call this inside of main. So we could decide to say, let's see the result of printing, running quadratic, and passing in, let's say we want to do 3x squared plus 2x minus 5. And we're going to call this function on a value of x that's equal to 2. Okay? And you can work out the math of what that should be, but when we run it, we'll get 11. All right? So functions can take multiple parameters. If the parameters have the same type and they occur consecutively, we can get rid of all these declarations that they're integers. And Go will just assume that a, b, c, and x are all type ints, since we put that int after all 4. So to just demonstrate, I can run this again, and we get the same result. You can also have functions that return multiple values. So you might have a function that, for example, is called translate point. And the idea of this function is that it's going to take in two coordinates, x and y. So let's assume they're integer coordinates. Okay, and then it's going to take in an amount by which we're going to translate this point in the x direction as well as in the y direction. So we could call this a delta x and a delta y as ints. And so all of these are ints, so we can group them all together. And the result of translating this point is going to give us a new point, which can be represented as 2 ints. And again, to make this more general, we could use float 64s. So the return type of this function is going to be 2 ints, which we represent as that ordered pair. And here what we'll return is the result of translating this. So we need to return x plus delta x and y plus delta y. Okay, and I don't need that parentheses there. Okay. So I mentioned that we can group these parameter types. It would be just as fine to say x int, y int, delta x int. We also don't necessarily need to have functions that take any parameters at all. So we could write some silly function called pi that returns an int and returns 3. Not a very good function if we wanted to represent mathematical pi at all, but it's still an acceptable function. So we could define, let's say, e or p as equal to pi. All right, because the return type of the function pi, which takes no parameters, is an int. So if we print p, then we should see 3. Now, just as a note, I'm going to comment out or tell Go to ignore all these lines. And I can do that by putting a /* on the first line I want Go to ignore, and a */ on the last line that I want Go to ignore, and everything in between those comments is going to be ignored. So that way I can see what we're getting. And so I'm verifying that p was in fact assigned the value 3, which was the output of this function pi that we wrote, and I printed p to show you that. Okay. Not only do functions not need to take any parameters, it may be the case that they don't return anything at all. So one would be if we have, say, a function that where we just want to print the square of some x int. Okay, we don't actually want to return a value. We just want to print it to the console. And so we might put this into a nice English sentence. So I might say x and then concatenate that with squared is, and remember when we put commas we add a space between in the print statement, and let's say square of x. Okay, so this takes a value of x and it doesn't return anything. All right, so if we just call print square of, let's say, 5, we should get 25. All right, so 5 squared is 25. The key thing to think about here then is what is the difference between printing and returning, really? the way I would think about it is that printing is a very narrowly defined idea in which we're only printing something to the console. The idea of a function returning a value is much more powerful because you can have hundreds of functions that can communicate in various different ways, returning different values and passing those as inputs to other functions, and kind of having a network of functions that interact in this way. Printing is just printing something to the console, and as we do more programming, you'll see that programming moves beyond printing relatively quickly. So I want to make sure that you understand the difference between these, and it's another reason why we start with, on the pseudocode level, and thinking about functions as having an input and an output. That's just a generic idea that's independent of printing anything to the console, because students often ask the first time that they start programming about the difference between returning and printing, and get this kind of confused. And so I want to point this out. If you're looking for an analogy here, a good one would be that if you're driving a car, it may have some fancy console that prints out, what radio station you're on, or what speed you're going at any given time. And this is a very narrowly defined operation of printing something to the user. Whereas all the functions of the car, you think of all the internal systems of the car that are interacting with each other, there's input and output processes that are going on all the time that you aren't necessarily noticing when you look at the console of the car. So this is the same kind of general idea, where we're thinking about a function as something a lot more general than just something that's doing a printing operation. Back to the narrative, you'll have noticed that the main function is in fact a function. So the runnable component of your program is a function, and that function takes no input and has no output. So it is possible to define a function that has no input or output. Main is probably the one function that you're going to use that does this. And so the only other thing that I would have to say here is that you'll note that we've been including package main as the line at the start of our programs. We're going to go more in depth into this later. For now, I just want you to think of this statement as an indication to go that somewhere later in our code we're going to have a func main that corresponds to the runnable part of our code. Okay, so otherwise, that's essentially the basics of functions. There are just a few other things that I wanted to say about them. One is that if we continue the analogy of thinking about programming as having a style, much like writing, we'll think of the functions as then the paragraphs of programming. So as when you're writing a paragraph, a function should be well written, but each one should also cover one single short idea. You shouldn't have a paragraph that spans 3 pages long. The start of the function, what's called the function signature, or the name of the function plus its parameters, we can think of as the topic sentence, or the first sentence of a paragraph that indicates, kind of essentially gives a general idea of what that paragraph is going to be about. And then just as paragraphs flow together and tie together into, say, a chapter of a novel, the function should tie in nicely, so to speak, with the rest of your program, and there should be a nice flow, and it should be easy to read and understand your program by seeing how it is on a high level that these functions interact. This is a skill that is not necessarily common in beginner programmers, and it's something that we want to try and cultivate over the span of this semester. So generally when people start programming, they have a single task, and they want to do that single task, regardless of how complex, as a single function that just does everything. And so I want you to constantly think about ways in which you can what's called modularize, or make your code so that each function is relatively short and that functions call each other. Okay? So if you look at a distribution of a typical program in Go that's well written, you'll actually see many short functions that constantly call each other. And this makes the program really easy to read because the functions are very straightforward and it's clear what each function does individually, and they try to break the large program into a lot of small pieces. Another thing that we've started thinking about in terms of how to break this into small pieces is to think about the program on the highest level first. And again, this is something that I understand when you start programming is not a natural thing to think about, but is something that we're going to try to do over the course of the term. Okay, so thinking about at the highest level first, and then asking yourself what subroutines or what functions you're going to need as you go down through the program is going to be called top-down design. And it's something that I've mentioned, and it's something that we've seen already when we devised pseudocode for the frequent words problem. Okay, we came up with a very high-level algorithm, and we assumed that we had a substring, a count, a max, and a remove duplicates subroutine that had been written for us. And then we assume, well, we can write those as we go down from the highest level of abstraction down the chain to get to simpler tasks. All right. One other thing that I would say on how we name functions as well as how we name variables. Make sure that you use names that are as descriptive as possible. So if you have an integer n, for example, and it represents a number of people, you might use the variable name num of people. It's important to note that the variable names are case sensitive. So lowercase n is going to be a different variable than n, and if we capitalize certain letters in num of people, that's different than if we don't capitalize them. The exception to this is that if you're using some integer that's not lasting very long in your program, for example, some index over a for loop, you're going to use a single letter like an I, J, or a K. For readability, I have a note in there on Camelcase where when you start a new word, if you have a variable or a function name that's multiple words long and you want to squash these together into a single string to name the function or name the variable, use what's called Camelcase, in which when you start a new word inside of that string or inside of that variable function name, you use a capital letter. Okay, so that indicates where the breaks between the words are. Good function names are usually going to involve verbs. So the first word in a function name is typically going to indicate what the verb is that's going on. Are we printing a full name? Are we encoding a single read? Are we listing buckets, etc.? Whatever it is that we're doing, it's good to indicate the first word with a verb. Generally, we're going to start variable names with a lowercase letter, and we're going to start function names with an uppercase letter. We'll see exceptions to this. I've already given examples of functions that I started with a lowercase letter. For now, you can do it as lowercase or uppercase letter. I would focus on just assuming that your functions are going to have an uppercase letter. And then the final thing is there's nothing wrong with having longish variable or function names. So don't feel like you have to use abbreviations that when you go back to your code, if you're, say, studying for a midterm 2 weeks later, you might not actually understand what that abbreviation was when you came up with it, let alone if you wrote a huge program that somebody else had to come in and understand 9 months later. Okay, so that's all I would have to say on variables and functions, and we'll connect this to what we're going to talk about next, which is coming back and thinking about how it is that we're going to implement if and else statements in Go. So now that we've learned a little bit about variables and functions, let's come back and talk about if-else statements and how we might implement those in Go. So where I wanted to start was with a simple computational problem, which says, take two integers a and b as input and return the greatest common divisor of a and b. So just as a warm-up for this, I'd like you to design an algorithm on the pseudocode level to solve this problem. Pause the video, take a couple minutes to write this up, and then play the video again, and we'll start again. So one idea that you might have would be to note that it's not possible for the greatest common divisor of a and b to be larger than the minimum of the two numbers. So what we can do is simply try every number less than this minimum and take the greatest common divisor that we find. Okay, so we might have a function GCD that takes input a and b. It sets a GCD variable equal to 1. It sets m equal to the minimum of the two input variables. And then there's a simple for loop that just goes through and says if start p, say at 1, and range it up to m, and for each p, if you find that p is a divisor of both a and b, so if a divided by p and b divided by p are both integers, update your GCD variable to be equal to this divisor p, and then at the end of this for loop, the largest one that we've updated has to be the greatest common divisor of the two numbers a and b. All right. Another idea that we could have would be to note that if we start with the minimum of a and b, we don't need to necessarily go from 1 up to the minimum. So we could start at the minimum and then move downward and simply return the first common divisor of a and b that we find. All right, so the first one that we find when we go from the minimum of a and b downward has to be the greatest common divisor. All right, so we would set here m equal the minimum of a and b, and then we'd have a for loop that ranges through every number p starting at m and then going decreasing down towards 1. We would test, again, if a and both have p as a divisor. So if a divided by b and p divided by p are both integers, then we would return this number p, since we know it has to be the greatest common divisor of a and b. All right. There's another way of doing this, which is ode to Euclid, and some people have called it essentially the world's first non-trivial algorithm. So the first precise method for doing something that was based in something that wasn't obvious, or that was and that essentially is founded on a mathematical idea. And that mathematical idea is a simple theorem that says if a is larger than b, then the greatest common divisor of a and b is equal to the greatest common divisor of b with a minus b. And so to show an example of why this might make the algorithm quick, you could start with, say, trying to find the GCD of 378 and 273. And because 378 is bigger than 273, we know that the GCD has to then be the same as the GCD of 378 minus 273, or 105, and 273. Again, 273 is larger than 105, so that GCD is the same as the GCD of 105 and 273 minus 105, which is 168. And so we can iterate this process to say that's the GCD of 105 and 63. Then say, what's 105 minus 63? Well, that's 42. So that's the GCD of 42 and 63. 63 minus 42 is 21. And now we're starting to see that this is converging to something. 42 minus 21 is 21. And the GCD of 21 and 21 is, of course, just 21. And we get that as our answer. All right, so rather than having to test a huge number of possible divisors, we were able to kind of narrow down on the GCD very quickly using this idea. And this isn't a math class, so if you're interested in seeing why this theorem is true, feel free to take a look at Wikipedia or a math website. But we're interested in this on a programming level, and because it's making our algorithm a lot quicker. But if we're just if we're able to not have to consider every possible divisor of two numbers a and b, but we can drill down and get to the greatest common divisor using this theorem a little bit quicker. So again, we'll take a couple minutes, use this idea to implement Euclid's algorithm on the pseudocode level, and then we're going to transition towards actually implementing this in Go. So one way of solving this would be to use recursion. And so to recall recursion, I want to recall this recursive Gauss program that we wrote before, where we had an integer n as our input, and if n was equal to 0, we simply returned 0. Otherwise, we returned n plus the result of calling recursive Gauss of n minus 1. So in effect, what we did was contract out the result of summing the first n minus 1 integers, or n minus 1 positive integers, and then simply adding n to that. All right, and this resulted in calling subsequently recursive Gauss on subsequently smaller inputs until we got down to 0, in which case we returned 0, and this kind of sprung up the chain and summed 1 plus 2 plus 3 plus 4, etc. up to n. All right, so we could use a similar idea for recursive Euclid. So in this case, what's in essence is our base case is if a is equal to b. And if that's the case, then we could return b, return a, they're the same. Otherwise, if a is greater than b, then we would simply return recursive Euclid of a minus b, which is what the theorem states. Otherwise, so we have an if, else if, and an else. The third case is if b is greater than a, and we'd simply return recursive Euclid of b minus a and a. Okay, so this is essentially how we're subcontracting the work, is applying this theorem to continually go towards a smaller input size. So if a is greater than b, then we subtract a minus b and find the GCD with b. If b is greater than a, then we find the GCD of b minus a and a. And both of those are simply using the theorem. And eventually, in this way, we're going to get down to a base case in which we call recursive Euclid of two things that are the same. And I'll let you play around with that and reason out why that's the case. In which case, we have the case that a is equal to b, and that is simply going to return a. And here we're not adding anything or doing anything with these different recursive calls. At the very bottom of this chain of recursion, we're going to return a, and that's going to return a up all of those calls that we had stored, eventually till we get to the original call of what we were running recursive Euclid on, and that's going to go all the way up to the top. Okay, so let's then take a look at this in Go and try to implement this recursive Euclid function there. So let's define a function, and we could call it GCD, and it's going to take two int variables, a and b, as its parameters, and it will return an int as well. Okay, so there's the overall structure of the function, and I encourage you to think through functions in this way and to write them in this way where you write the first line all at once, thinking through what the input types and output types are, and bracket off your function accordingly. Okay, so we're going to have an if statement, and how if statements are going to look in Go is they'll have a generic structure where we have an if. If we have an else if, we'll have this structure, and I'm going to fill in, this is essentially just the skeleton of the if else if, and then we'll have an else, and we're bracketing it off in this way. Okay, so we could have if a is equal to b, and now in Go, Go is interpreting a equal to b as take a and assign it the value stored within the variable b. If we're testing whether these two values are the same in these variables, we're simply going to use a double equals so that we have Go can interpret this as two different things. All right, so if a is equal to the value stored in b, then we could return a, we could return b, doesn't matter. Okay, so that's our base case of sorts. Otherwise, we were going to test if a was bigger than b, and that works the same in Go. And in this case, we were going to simply return the GCD of a minus b and b. All right, and then the final case, and I could add a comment here to indicate, well, in this case, we must know that b is greater than a. Well, we would return GCD of b minus a and a. Okay, and commenting can be helpful. We may even want to add a comment at the beginning of our function describing it. So we could say GCD of a and b computes the greatest common divisor of a and b. All right. And so you see the same structure of the function that we had before. Now we understand kind of how if and else statements are going to work. I would give you a short exercise, which is, let's write a function called factorial. And it's going to take an integer n and return an integer. And what factorial is going to do is simply returns n factorial, which is n times n minus 1 times dot 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 times 2 times 1. Okay, so take a second and implement this function in Go, and with the caveat that it should be recursive. And I'll see you on the other side. What we might do then is to have a base case saying if n is equal to 1, then we're simply going to return 1. Otherwise, the subcontracting that we would do would be to say we'll return n times the result of calling factorial of n minus 1. So that should be a relatively simple exercise. It's just to get you comfortable with typing in if-else statements in Go, and just a quick refresher of the types of things that we do with recursion. All right, as a sanity check, we could come down here and print out factorial of 5 and verify that indeed that's 120. We could also do GCD of 378 and 273, which was our example before, and print those, and that gives 21, okay, which is what we saw before. So another thing I wanted to say was, let me point out, say that we had decided to write this GCD function, and I'll call it another GCD. It took a and b as integers, and it returned an int. Okay, so it said if a is equal to b, we're going to return A. Else if A is greater than B. And the slight modification I want to make is say that we had declared C as an integer and said that C was equal to A minus B, because this is the case that A is bigger than B. And in this case, we would return another GCD, since that's our function in here, of C and B. All right, and there's no real compelling reason to do this. I'm just using this to illustrate a point, which will become clear soon enough. Otherwise, we're going to have C is equal to B minus A. And this is our B is greater than A case. So C is B minus A, and we're going to return the result of GCD of A and C. Okay, so very similar setup. All we're doing is introducing this C variable beforehand, before actually making the recursive call. All right, and we could run this, and we're going to get a compiler error here. So the issue would be, why do we think that this happened? You could take a moment if you want and just hit pause. I'll go ahead and tell you that the reason is that if we look at line 35, where things are going wrong, it's telling us that C is undefined. And we know that we've defined C in this block, right? So that may be confusing to us initially, since we see, well, we defined C on line 31. But the issue here is that variables only last from essentially the beginning to the end of the block in which they're defined. So C was defined inside of this block, which lasted here. Okay, so we can only actually refer to C in this area. After this point, so as soon as the block ends, the variable is destroyed. So we could get away with this by either adding another varcient here, which would redefine C. So they would essentially be two completely different variables, even though they have the same name. Or we could define varcient here and remove that line. And the scope of this C would be from that block to that block, since it's kind of inside, at the highest level inside of the function. And if we were to run that there, we wouldn't get a compiler error, and so we could actually just say, let's do another GCD, and we should get 21 there as well, which we do. Okay. So again, another thing we could do would be to say, look, we could move this variable definition to here. And again, this is not necessarily very good coding practice to define these variables in two different places, or to even need this C variable in the first place. But if we were to do this, everything would be okay, because this C would be defined from this block to, or that bracket to that bracket inside of that block, and this C would be defined inside of this block. All right, so everything would be okay there. One thing we wouldn't want to do, or we'd get another problem, is if we defined C outside there as a variable that has a lifestyle inside of the outer block of the function, but we then redefine it inside of another block. So the problem there is, if we run it, we get a compiler issue there, and that would be that C is declared and not used. Another way of seeing it, so it's declared on the very outside, so this C variable is created, and then a brand new C variable is created inside of this block and inside of this block. And so it's saying, well, this C variable that you created at the beginning to have this kind of function level life never actually got used. Okay, so it's as if we named it something completely different, like D, we'd get the same thing. All right, so it's important to think of the scope of a variable once you introduce it. You want the variable to have the appropriate scope. So you don't want it to be too limited. You don't want a variable that's introduced in a tiny block and then is needed elsewhere in the function. And you also don't want a variable that you declare at the very beginning of the function. Say, if you wanted a variable I that was only going to last for 2 or 3 lines later on in the function, you wouldn't necessarily want to introduce that at the very beginning of the function, because maybe you would want to call multiple things I in like subblocks of your function. And so that's not good coding practice either. It's good to declare your variables at the kind of appropriate scope. so in the right block that they're needed. There's one other thing that I wanted to say here, which is that when you look at the parameters of a function, they have scope that begins at the beginning block of the function and ends at the last block of the function. This makes sense, essentially, since if we call a function, so if we call another GCD of 378 and 273, essentially there are two variables created somewhere in the computer with values 378 and 273, and they last for as long as the function was called. So in the main function, we don't actually really see this much, but somewhere in the computer the function is called, these variables are created. They are given the values associated with 378 and 273, and they last as long as the function is needed. Okay, so it's a good way of thinking about kind of how the computer is going through this process. The function is called, it moves to some other place in the computer, and it goes through the function and then comes back to the next line in main. This is something that we'll get a lot more in depth in much later in the course when we come back to thinking about how to represent what the computer is doing on an assembly language level or in terms of the actual memory allocation of creating variables and how we store them. For now, I'd like to come back to the PowerPoint and say something about additional conditions. So we started working with testing if something is greater than something else or less than or equal to something else. And equality uses this double equals if we're testing an if or an else if. We also have a bang equals or an exclamation mark equals that says to test if expression 1 is not equal to E2. And these don't have to be individual variables, they can be entire expressions. Okay, so we could test A versus 10 times B plus C, right? And that tests whether A is greater than the expression on the right side of that equation. And so on. The not is going to be essentially true precisely when the expression is false. So if we're testing not x times y is less than 33, that's true precisely when x times y is greater than or equal to 33. Okay, so it's the equivalent condition that we would be testing there. And all these expressions are called Boolean expressions, which, as you might guess, is because they evaluate to either true or false. All right, so the other thing that we would like to do, though, is to test multiple things at the same time. So maybe we want to test whether A is less than 2 and B is greater than some variable C plus 6. All right, and if we want to test both of those things at the same time, we might use an AND statement. And we can represent AND of two Boolean expressions using a double ampersand. All right, so essentially expression 1 double ampersand expression 2 represents a larger expression that's going to be true precisely when each individual expression is true. So E1 has to be true and E2 has to evaluate to be true. If we're looking at something that would be an OR, so if only one of them needs to be true, or it could be the case that both of them are true, then we would use a pipe character, which is often above the backslash on the keyboard or the shift backslash. So that would be true precisely when either E1 is true, E2 is true, or both of them are true. So it's not, we don't think of this as the exclusive OR in that you can have either cake or ice cream for dessert. We think of it in an inclusive sense, so either expression could be true or both could be true, and in that case the overall Boolean expression E1 or E2 is also true as well. So when we start combining all these operators together into huge expressions, we need to know, if we're not parenthesizing these expressions, how is it that Go is going to prioritize the order of operations? And what Go is going to do is it's going to proceed very mathematically here. So at the highest level, which is precedence level 5, we would have the multiplication symbol, division, as well as percent, which I'm going to cover shortly. So if we were looking at this expression, the first thing that you would do is you'd multiply 2 times A times C, 3 divided by Z, A divided by 2. The next level you go to, of course, same as math, you go to addition and subtraction. The next level is you would test. Now we've got these Boolean operators that we would test. So we would test equality. So we would say, is it the case that 2 times A plus B is not equal to 3? And then we would look at, is it the case that A times C minus 3 over Z is less than -5, and so on. All right. And then we're moving lower. We have the and the or. And so we need to know which one of these we do first. And so in this sense, you can think about there being like a hidden set of parentheses here, Okay, just as in this previous step, there's essentially a hidden set of parentheses here, and here, and here. In this one, we do the and first. All right, so there's parentheses there, and then we would do or. We're perfectly allowed to use parentheses to force a different order if that's what we mean. And so if you're ever in doubt, feel free to use parentheses to force whatever order you're looking for. So if we wanted this or operation to happen first, we would put the parentheses there, and then we would take the and of this Boolean expression as well as the result of taking this Boolean expression. So this is a pretty complicated expression that we probably aren't going to see in this class, but it's just an example to show how all of these operators would relate to each other in terms of having an order of operator precedence. So let's just do kind of a true-false quiz just to make sure we're all on the same page. I'll give you a second to think through this and do all of them, and then I'll go through them one at a time. Okay, so now that you've had a chance to do this true-false quiz, I'm going to show all the answers. If there's any major discrepancies or you still don't have a good understanding here, please feel free to let me know. The two that would tend to trip people up would be, one, remember that the single equals is used for setting a variable equal to some value. The double equals is used for testing equality, which are two different things. This one, remember that the and would be performed first in the absence of parentheses. So we would and together the test of A being equal to 10, which this is true, but B is not greater than or equal to 100. And so this entire and would be false. However, when we or that together with B equal to 50, that Boolean expression is true, and so the entire expression becomes true. All right, and so I'd like to come back to the playground and do a couple of other things just to finish up. So the first thing I'd like to do would be to write a function called smallest even. And let me say what it's going to do first. All right, so smallest even is going to say smallest even returns, I'll say of A and B, returns the smallest even number between two ints, I could use another line, A and B. If they're both odd, let's return 0. All right, so our smallest even function is going to need to take A and B as ints, and it's going to return an int, of course. And so we need to use what we've learned here. So the first thing we want to test is if A is even and B is even, that's really the case that we're going to have to do the most testing. All right, so A being even, you'll mention that I referenced this percent operator, and what the percent operator does is it takes the remainder. So I could say, let's see, x percent y takes the remainder when dividing an integer x by y. All right. So if we're looking to test if something is even, then we can simply percent it by 2, right? And if that remainder is equal to 0, then we know it's even. If that remainder is 1, we know it's odd. All right, so we can test if A is even and B is even by simply saying if. We're going to have a big if statement. All right, so A being even is A percent 2 equal to 0. And so we're testing if B is even as well, so we use the double ampersand, B percent 2 equal to 0 as well. All right. The other, and I'm going to fill in here in a second, the other case would be if A is even, but B is odd. All right, and I'm going to fill that in. So A is even, B is odd. All right, we'll have another one representing, and so everything after I add the double lines is commented out, the double slash marks. So this would be B is even, A is odd, and then we're going to have an else statement and this is going to be where they're both odd. And we said we're going to return 0 in that case. All right, so again, I'm thinking of this on the highest possible level, and then I'm going to delve into each of the individual if and else if statements. All right, so the first thing we would do would be to say, if we know that A is even and B is even, then we'd simply have a nested if statement to say, look, if A is less than B, because we're returning the smallest even number between them. So if they're both even, if A is less than B, we simply return A. Otherwise, we're going to return B. In the case that A is even and B is odd, well, we need to test something. So we could say A%2 is equal to 0 and B%2 is equal to 1. And we do something similar down here. So we'd say A%2 is equal to 1 and B%2 is equal to 0. However, if we get to this point, we know it's not the case that A is even and B is even. So if we're testing that A is even, which is what A%2 is equal to 0 is saying, if it reaches this point, then it can't be the case that B%2 is equal to 0. Otherwise, we would have entered this part of the if statement. All right, so we actually don't need that test, which is redundant. And in particular, if we get to here, we don't need that test either. So if we know that that B is even, then we've reached here, then it can't be the case that A was even, or else we would have entered that part. All right, so just a minor point there in terms of making the code just a little bit shorter, but there's nothing wrong with having the and symbol there as well. All right, so returning back to our code, this is the case that A is even and B is odd. All right, so if A is even and B is odd, well, we return A, since that's the smallest even one of the two. If B is even and A is odd, we return B, and that gives us our function. All right. That's one function that I wanted to do. We could write this in a slightly different way using something called a switch statement, which draws its analogy from a railroad switch when we're switching lines on a railroad. So function, let's call it another smallest even. And I'm not going to test these functions. I can leave that to you, that they're actually doing the right thing. So how this would work would be to say we have a switch, and the switch is essentially saying we're going to have a big if, else if, else if, else if, else if, else. So if you have a really long set of else ifs, you might use a switch. So we would have a case A%2 equal to 0 and B%2 equal to 0. And so that case essentially just is the same thing as saying if A%2 is equal to 0 and B%2 is equal to 0. And we would then have an if A is less than B, return A. This is the same we did before, else, return B. Okay, so this is viewing the if else if as a sequence of distinct cases, and so we simply replace the else ifs that we had before. So we had case A%2 equal to 0, so we knew that B was odd in that case, and we use a colon again, and in this case we return A, excuse me. And then we had a case B%2 equal to 0, and that was where we returned B. And then we need a default case, and the default case is essentially the else. So in that case we return 0, and we need a closing bracket to indicate the end of the switch, which I already actually had in there. And so that's just a slightly different way of doing if and else if. Another example of this would be something like, say we wanted, and here's an example of where it can be useful. Say we wanted to write some function keyday that takes the month as input between 1 and 12. And what it does is it returns the key doomsday of the month, or the day of the month that we remember as part of this mnemonic device as being on the same day of the week. So our function would be key day. It would take a month value as an integer, and it's going to return an int, which is the day of the month that we're trying to remember. So we would switch based off of the month. All right. And based off of that month value, if the month is equal to 1, we would return, say, 31, because we remember January 31st. If month is equal to 2, then we might remember, for this year, February 29th. If the month is 3, we return 0, because we remember March 0th, and so on. So 4 was returned 4, and I'm just going to say etc. All right. In this case, we might want to say keep note of an error. So we might have a default case, and that default case could be at the end. We would just say default return -1, something like this. Since we would know that value would never be returned because of normal behavior of the function. One other, just kind of to beat a dead horse here and illustrate the switch statement again, we could have a skew value function, and it could compute the contribution of an individual nucleotide to the computation of GC skew. And I'll have you take a look at the PowerPoint handout. You'll remember that when we draw the skew diagram, every time you encounter a G, you simply go up by 1. Every time you encounter a C, you go down by 1. So this would be like a subroutine that we might use. So skew value would take a symbol. It could take a byte, or it could take a string. It's kind of up to you. And it's going to return an int. And so all it's going to return is +1 if it's a G, -1 if it's a C, 0 otherwise. All right, so we would switch based off of the symbol. And we would have case A return 0. Case T is also a return 0. And I said in the case of G, we return 1, since we increase by 1. In the case of C, we decrease by 1, and I'm not going to put a default on that one. All right, so that's everything I can say about conditionals, which comprised in Go if and else statements, as well as these switch statements as well, which can be helpful. So I plan on seeing you on Monday's lecture. I look forward to that, and enjoy the weekend.